Have you ever been working on your computer, clicking away, and then nothing? The mouse moves, but nothing responds. It's like the entire system just decided to hold its breath and refuse to do anything. What if I told you that a lot of the time this isn't a crash? It's a tiny, perfect, logical traffic jam happening deep inside the machine. A digital standoff so complete it can bring everything to a grinding halt. Well, today we're going to dive deep into that paralysis. Today we will deeply understand Chapter 7, Deadlocks.
So here's our roadmap. First, we're going to really define what this digital traffic jam is all about. Then, we'll become detectives and identify the 4 essential conditions that have to be present for this gridlock to even happen. Once we know the causes, we'll explore the 3 main strategies operating systems can use to fight back. Prevention, which is like designing a city with no intersections. Avoidance, which is like having a super smart traffic controller. And finally, detection and recovery, which is basically sending in the tow trucks after a crash has already happened. And we'll finish up with the big reveal. What do the systems you and I use every single day actually do about this problem? The answer might surprise you.
All right, let's get right to the heart of it. What exactly is a deadlock when we're talking about computers?
You know, sometimes the best analogy comes from the most unexpected place. This right here is an actual law passed in Kansas over a century ago, and it's a perfect real-world recipe for a deadlock. You have 2 trains, both needing the same resource, the crossing. The rule says neither can move until the other one has. Just think about that for a second. The result? A permanent, legally enforced standoff. Those trains aren't going anywhere, ever. And that, in a nutshell, is the exact same logical trap that happens inside your computer.
So let's translate this into computer terms. Instead of trains, we have processes. You can think of a process as any program that's running, like your web browser, a video game, or even a background system task. And instead of a train crossing, they're competing for resources. Things like access to the printer, a specific file on your hard drive, or a chunk of system memory. A deadlock, then, is this situation where a set of these processes are completely stuck. Why? Because each one is holding onto a resource that another process in the group needs, while at the same time it's waiting for a resource that another process is holding onto. It's a digital circle of waiting, and nobody can make the next move.
So how can we, as computer scientists, actually see this happening? Well, we draw a map. It's called a resource allocation graph, and it's a super useful way to visualize the state of the system. Let's picture it. Every running program, every process, is a circle, and every resource, like a printer or a file, is a square. Now, if a process wants a resource, we draw an arrow from the circle to the square. That's a request arrow. Once the process gets the resource and is using it, we flip the arrow's direction. Now it goes from the resource square to the process circle. That's a hold or assignment arrow. Here's the key part. If you can trace a path of these arrows that starts at a process and eventually leads you right back to it, well, you've found a cycle. And a cycle in this graph is a huge flashing red light that screams potential deadlock.
Okay, so this is really important to understand. A deadlock isn't just some freak accident. It's a very specific kind of failure that can only happen if 4 very specific conditions are true at the exact same moment. If even one of these conditions is missing, a deadlock is impossible. So let's break down these 4 culprits.
First up, we have mutual exclusion. This is just a fancy term for the simple fact that some resources, by their very nature, can't be used by more than one process at the same time. A printer is the classic example, right? You can't have 2 different documents printing on the same sheet of paper simultaneously. The output would be garbage. So the operating system has to enforce this rule. Only one process gets access at a time. The resource is mutually exclusive.
The second condition is called hold and wait. This is exactly what it sounds like. A process is already holding on to at least one resource, but it needs another one to continue its job, and that other resource isn't available right now. So what does the process do? It just sits there, holding on to what it's got, and waits. It won't let go of its current resource until it gets the new one it's waiting for. It's both greedy and needy at the same time.
Third, we need the condition of no preemption. Preemption means to take something away. So, no preemption means that once a process has been granted a resource, the operating system can't just swoop in and forcibly take it back. The process is the boss of that resource. It will only release it voluntarily when it's completely finished with it. You can't just snatch a file away from a program while it's in the middle of writing to it. That would cause chaos.
And finally, the 4th condition, the one that ties this whole mess together. Circular wait. This is where you get a chain of waiting processes. Imagine process A is waiting for a resource that process B has, but at the same time, process B is waiting for a resource that process A has. You see the circle?
It can involve more than two processes, of course. A could wait for B, who waits for C, who waits for A. It's this closed loop of dependencies that creates the unbreakable standoff. When all four of these conditions, mutual exclusion, hold and wait, no preemption, and circular wait, are met, you've got yourself a deadlock.
So, if we know the 4 ingredients required to bake a deadlock cake, the most straightforward strategy is just to design an operating system that makes sure one of those ingredients is always missing. This is what we call deadlock prevention. We build the rules of the system to make deadlocks structurally impossible.
So how do we do that? Well, we can try to attack each of the 4 conditions. We could try to eliminate mutual exclusion by making everything shareable. But like we said, that's just not possible for things like printers. Or we could attack hold and wait. We could make a rule that says a process has to request every single resource it will ever need right at the very beginning. But that's incredibly inefficient. A program might hold on to a printer for hours, even if it only needs it for the last 5 seconds of its run. What about no preemption? We could let the OS forcibly take resources. But this is really complex to implement correctly and can lead to corrupted data. So that leaves us with circular wait. And this is where we find a practical solution. We can break the possibility of a circle by imposing a strict order. We number all the resources in the system, 1, 2, 3, and so on. Then we make a rule. Processes can request resources in any order they want as long as it's an increasing order. You can't ask for resource 5 and then ask for resource 2. By enforcing this hierarchy, a circular wait becomes impossible.
Now, prevention is effective, but it can be really restrictive and hurt system performance. So there's a more dynamic and clever approach called Deadlock Avoidance. Here, the operating system doesn't have hard and fast rules that prevent deadlocks. Instead, it makes intelligent decisions in real time to make sure it never even enters a state where a deadlock could potentially happen.
The core idea behind avoidance is the concept of a safe state. Think of it this way. A safe state is one where the operating system knows there is some sequence of running processes that will allow every single one to finish its job without getting deadlocked. An unsafe state, on the other hand, is a state where a deadlock might happen. It's not a deadlock yet, but the system has allocated resources in such a way that it can no longer guarantee that everyone can finish. The goal of a deadlock avoidance algorithm is to only make resource allocations that keep the system in a safe state.
And the most famous algorithm for this is the banker's algorithm. The analogy is perfect. The operating system is a banker. The resources, let's say we have 3 types, A, B, and C, are the banker's money. The processes are customers. Before any customer starts, they have to declare their maximum possible loan. That's the max column you see. The allocation column shows how much money each customer currently has borrowed. And that available row at the bottom, that's the cash the banker has on hand right now. The banker's job is to grant new loan requests only if they know that even after granting the loan, they'll still be in a safe state where they can satisfy all their customers.
So how does the banker figure out if a state is safe? It runs a simulation called the safety algorithm. It's basically a thought experiment. First, it pretends it has a certain amount of cash to work with, which is equal to what's currently available. Then it looks for a customer whose remaining need, that's their max minus what they already have, is less than or equal to the cash on hand. If it finds one, it pretends to give that customer the loan. It assumes that customer will now finish their job and, this is key, pay back their entire loan. The banker adds that full loan amount back to its pile of work cash. Then it repeats the process, looking for another customer it can satisfy with its now larger pile of cash. If the banker can find a sequence where every single customer can be satisfied and finish, the state is safe.
So now let's put it all together. A process makes a new request for resources. What does the OS, our banker, do? First, it does some basic checks. Is the request valid? Do we even have enough available resources right now? If those checks pass, it moves into a hypothetical world. It pretends to grant the request. It updates all the numbers. The process's allocation goes up, the available resources go down, but only in its imagination. Then, on this imaginary future state, it runs the full safety algorithm we just talked about. If that algorithm comes back and says, yes, this hypothetical future is safe, then and only then does the OS actually grant the resource request in the real world. If the hypothetical future is unsafe, the OS says, nope, sorry, and makes the process wait.
Okay, so we've covered prevention and avoidance. But what if you have a system where those are too expensive or too restrictive? The third option is to just let deadlocks happen. You don't try to stop them. You just have a system in place to periodically check if a deadlock has occurred, and if it has, you take steps to fix it. This is the detect and recover strategy.
So, how do we detect a deadlock?
Well, if you have a system where there's only one of each type of resource, one printer, one DVD drive, and so on, we can use a simplified version of our resource map called a wait-for graph. It's much simpler. We don't even draw the resources. We just draw the processes, our circles. And we draw an arrow from process A to process B if A is currently waiting for a resource that B is holding. If you run your detection algorithm and find a cycle in this graph, it's not a warning anymore, it's a guarantee. A cycle in a wait-for graph means you have a deadlock, right here, right now.
Once you've detected a deadlock, you have to break it, and the options for recovery are, well, pretty brutal. There are two main approaches. The first is process termination. This is the simplest. You can either use the sledgehammer approach and just abort all the processes involved in the deadlock, or you can try to be more surgical and kill them off one by one until the deadlock cycle is broken. The other option is resource preemption. This is where the OS forcibly takes a resource away from one process, we call it the victim, and gives it to another to break the cycle. But this is really tricky. You have to be able to roll the victim process back to some prior safe state, and you have to be careful not to keep picking the same victim over and over again, which could cause it to never finish its work, a problem we call starvation.
So we've explored these three intricate strategies: building walls to prevent deadlocks, intelligently steering around them, or cleaning up the mess after they happen. So the big question is, what do the operating systems we use every single day, Windows, Mac OS, Linux, what do they actually do?
And here's the big secret. After all of that complex theory, the most common method used in modern operating systems is to basically do nothing. It's often called the ostrich algorithm. And yeah, the name is a bit of a joke. The idea is you just stick your head in the sand and pretend the problem doesn't exist. Now, why on earth would they do that? It's a trade-off. It turns out that deadlocks in a general-purpose computer are a relatively rare event. The performance cost of running complex prevention or avoidance algorithms all the time is really high, and it would slow your computer down noticeably. So the engineers decided that a faster system that very rarely freezes is better than a much slower system that never does. It's a pragmatic choice of performance over perfect correctness.
And this brings us right back to our original question. Why does that classic piece of tech support advice, have you tried turning it off and on again, actually work so often? Well, because a reboot is the ultimate brute force deadlock recovery tool. It's the nuclear option. When you restart your computer, you don't just kill the deadlocked processes, you kill every process. You forcibly preempt every single resource and return the entire system back to its initial clean state. It completely wipes the slate clean, destroying the four conditions that allowed the deadlock to exist in the first place. It's not elegant, it's not sophisticated, but in the face of a perfect logical knot, it's an incredibly effective solution.